Okay, so make sure that you've read the question on your own. And if you look, they gave you an equation, which is W of t, right? Whoops, W of t right here. And they say that that is a rate, and it's a rate of water being pumped into the tank. If you keep reading, it says R of t is also a rate, but that's a rate of water being removed. Okay, so I'm going to just write those two things down. So this right here, that's supposed to be an arrow, is a rate, but that's a rate of, oops, that's an REM, short for remove. Okay, and then this W of t is also a rate. My pen's not working too well, but that's a rate of I'm going to just write in for short. Okay, so the rate that the water is going into the tank versus the rate that the water is coming out of the tank, which is R of t. Okay, so let's look at part A. It says estimate R prime of 2. Now remember, when we see this, we've talked about this when we did mean value theorem. So I know it doesn't really give you too much in the way of hints, but when you see R prime of t, and then what you have here in this case is R, then we're going to find out, we're looking for R prime of 2, so I know that 2 is right in here. So I'm going to use the values, the t values of 1 and 3. Okay, so we're going to do R of 3 minus R of 1, remember mean value theorem, over 3 minus 1. Now all you do is work it out, and you write your units. Okay, so I'll probably take a minute, pause me, and work this out. So that's going to give me 950 minus 1190 all over 2. So then my R prime of 2 would be negative 120. Now let's talk about the units here, because what we have in the chart itself, remember, this is already a rate, liters per hour. And what we are doing to that rate is taking its derivative. So if we have liters per hour, what is our derivative's units? Okay, so remember that that's going to be liters, and we always square the time unit. There's your answer. All right, so let's read the question. They're asking us to do a left Riemann sum, 4 subintervals, and we're estimating the total amount of water removed. And because it says removed, remember from part A, I hope you took notes in your packet, this R of t represents the rate of removal. All right, so let's start with 4 subintervals. So that means here's 1, here's 2, here's 3, and there's 4. Okay, now they want the left Riemann sum. So if you look, let's look at the very first interval here, and we see that the width of that rectangle is going to be 1. So I will have 1 times, and then the height, we're going to look at the left side, so 0 is the left, 1 is the right, so we're looking at the left side here, the left t value, and we go up to its height, which is 1340. So that will be 1 times 1340 plus, now let's go to the next grouping. So we have 1 and 3, so the distance from 1 to 3 is 2. And then 1 is the t value that's on the left, and we're going to use the 1190. So that means we're going to have 2 times 1190 plus, all right, what are we going to get on the next one? So the next one we're going to get 3 times 950, right? Oops, sorry, that looks gross, but that's a 950. And the last one is going to be 2 times 740. And then we are going to work this out. This is a calculator question, so you can put all of that in. All right, so pause me. Why don't you work that out and see what you get? Okay, so you should get 8,050, and this is an amount. What we have here, R of T represents liters per hour, which is a rate. But what we're essentially doing by a Riemann sum is we're integrating. So remember, that's always going to leave us with liters. Okay, now this was a two-part question because the second part says, is this 8,050 an overestimate or an underestimate for the total amount of water removed? So you know me, I always like to draw a picture. So, and it can just be a rough sketch, but if you really, what you should notice, let's see, we're going 1, then we're going to 3, then we're going to 6, and then we're going to 8. And here's the most important thing, guys, is it doesn't have to be the most gorgeous picture, but you can see that my graph is decreasing. And that really is the most important part, because watch what happens. So if I'm doing a left Riemann sum, remember the first interval is from 0 to 1. So I go to 0's height, which is 1340, go over, and make my first rectangle. Then I go to the next interval, which is between 1 and 3. Well, 1 is on the left side of that interval, so go up to its height, go over, draw your next rectangle, and so on, and so on. Okay, so you can see then, I hope that you can see that we've got an overestimate because these rectangles, and honestly, I didn't draw this really well. This will be over as well. We have an overestimate because our rectangles are above the curve, and that's all you have to say. So you're going to say that it's an overestimate because I'm going to abbreviate. The rectangles, are above the curve. All right, so let's read part C pretty carefully here. So it says to use your answer from part B. So part B, let's just write down that part B, we had we had the rate of removal, right? Or the amount of removal. Okay, so I'm going to write amount removed, and that was equivalent to 8050. Okay, so there's a reason why I want to have that there. So let's just think about this for a second though. So it's saying use your answer from part B, so that's this, to find an estimate, and this is going to be an estimate, of the total amount. Now total amount does not mean rate, so we should be thinking integral of some kind, okay? Total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so total amount of water in the tank, wouldn't that mean that we would have to which means then this little integral that I wrote, I'm going to actually, this one right here, what I'm going to do is I'm going to write 50,000 plus, and then I'll show the integral, okay? Because I'm starting with 50,000. And the question in part C is asking us to find an estimate of the total amount of water in the tank. So I had 50,000 to begin with. Now, let's integrate the rate going in. Well, remember, if you go and you look at part A, the rate going in would be represented by W of T. So W of T. And they said from time 0 to time 8, so 0 to 8. Okay, minus. Now, let's look at what we have here. So this right here is my integral of the rate going in. Now, integral of the rate going out is the amount that came out, but isn't this the amount that came out? Granted, it's an estimate, but this says to find the estimate, and it says you have to use your answer from part B, and that's why I wrote this down. So I don't have to integrate, because I already did that in part B, and they want me to use my part B answer, so all I'm going to put here is 8,050. So then really the only thing I'm responsible for is this. Now remember though, whoops, this is a calculator question, so you can put this in your calculator and get an answer because you have your W of t equation. So put W of t in your Y1, go to Math 9, go from 0 to 8, figure out what you get, and pause me. All right, so you should see what you get when you put that into your calculator. That's in red. And then we're just going to add the first two numbers up and subtract 8,050 from it, and we will get, let's see, 49,786 liters. Okay, so part D is saying between time 0 and 8, is there a time at which the rate at which the water being pumped into the tank, now remember, that's W of t, is the same as, in other words, equals, the rate at which the water is being removed. Now remember, that's R of t. So really, what they're asking, is there a time between 0 and 8 where W of t is equal to R of t? Is that ever going to be the case? From 0 to 8, that is. Okay, well, we do have a calculator. You should have the W of t equation in your Y1, so you could graph that, couldn't you? So if you look at the graph of W of t, it starts up at 2,000, and then by the time we get to 8, I'm just doing a rough sketch, but that's all you really need. By the time we get to 8, this value here, you can look at the table at time 8, and it would be 81 and change. Right, so 81 point, I think it's 524, something like that, 524. So now I'm going to do this. That's W of t. That's in black. All right, so now let's do R of t. Now, listen, I don't have an equation, so I can't really graph it per se, but I do have values. And look, I have this value at time 0, I know is at 1340. So then what that means is at time 0, my R of t is going to be below my W of t. Okay, hang on. Now, let's look at time 8. Time 8, my R of t is going to be 700. And look at where my W of t is at time 8. It's only at 81 and change. So what that means then is my R of t is going to be roughly somewhere up here-ish. Okay, and here's R of t, which means if I'm going to get from point A to point B, I'm going to have to come across W of t. And that's the most important thing that you need to see. Now, this is, again, really not the best sketch in the world, but it's going to look something like that. Okay, so again, the big thing that I want you to see is, look, there's got to be a point between 0 and 8 where W of t and R of t are going to be equal to each other. Okay, does that make sense to you? Because W of t starts high and ends up a lot lower than R of t. Granted, it starts lower, but it ends up higher. So it's got to cross over. Okay, so you can simply state, and this essentially is the intermediate value theorem that we did discuss. And intermediate value theorem just basically says that if, looking at the graph that we have here, so we're starting with, again, a graph that's higher and ends lower, and then another graph that starts lower and then goes higher. There's got to be a point in between, an intersection point, so to speak, between these two endpoints. And there would have to be at least one. Okay, so this would be our explanation.